Okay, our textbook only gives qualitative electrical fields, and I wanted to make sure that we understood that electrical fields are quantitative as well. They're not just nice little pictures that we have. All right, so this particular problem was one we did at the end of class, and many of you were halfway out the door for spring break, so I wanted to give you the opportunity to do this again. All right. The first question, part A, asks us to calculate the electric field at point A. Well, we see right here, point A is 1.40 meters above a positive 3.7 millicoulomb charge, and then that 3.7 is to the left of a negative 4.4 millicoulomb charge, which is also 1.40 meters away. So I have this isosceles right triangle right here. All right, so the first thing I want to do is I want to remember that the field at any point, remember that's a vector, is equal to K times the fixed charge divided by the radius squared. And you remember that K had a value of 9.0 times 10 to the 9th newtons times meters squared per coulomb squared. All right, so that should probably be saved in your calculator under K. All right, so when I'm at point A, I've got this positive charge here. Now what's that positive charge doing? That positive charge is creating a field away from it, right? It's pushing away, so out of the positive. So a positive charge placed here would be pushed upward at 90 degrees, and this negative charge down here, this negative charge would create a field towards it because that's a negative charge. So away and up. So I've got two vectors here that I'm going to be adding together. Let me go back to black. Okay, I've got two vectors that I'm going to be adding together. I don't know their magnitudes yet, but the first one is going to be upward, straight up at an angle of 90 degrees, straight up at an angle of 90 degrees, and the second one is going to be pointing this way, pulling this way at an angle of negative 45 degrees. And how do we add vectors? Head to tail. So I'm going to move that one up here. So once I know my magnitudes, I'll be able to make an estimate of my resulting vector from where you started to where you end up about that angle. So the first thing we're going to do is figure out the magnitude of the field that's pushing straight up. This positive 3.7 millicoulomb charge. So the field from that first charge is going to be K times 3.7 times 10 to the negative 3. 10 to the negative 3, that's millicoulombs, divided by 1.40 squared, r squared, and that turns out to be, 1.7 times 10 to the 7th, 10 to the 7th newtons per coulomb at an angle of 90 degrees. We already discussed that. A positive charge right here, a positive charge is going to create a field in that direction pushing directly upward. This negative charge right here, this negative charge is going to create a field down towards it, and that field is going to be K times 4.4 times 10 to the negative 3. The negative sign is not put in my equation, it's used to tell me the direction. Now r, what's the distance between here and here? What's the distance along that triangle right here? Well, it's going to be the square root of 1.40 squared, maybe square root of 1.40 squared plus 1.40 squared, Pythagorean theorem. That radius turns out to be 1.98 meters. All right, so that's what goes over here, 1.98 squared in that denominator. And now even though that's a larger charge, it's further away, and dividing by a larger number squared, it turns out to only be 1.0 times 10 to the 7th newtons per coulomb, and that angle is going to be a negative 45 degrees. So now I've got my two vectors and I've got their relative length. So let's draw it again. This time, back to my black pen if I could. There we go. Now I can draw this to scale. Now I can draw it to scale and make an estimate. Alright, my first one is, I would use a ruler and we're going to go up 17 centimeters. I'm going to measure up 17 centimeters. That's about right there. Okay. Let's see from here, 17 centimeters at an angle of 90 degrees. And this one I would measure 10 centimeters at an angle of negative 45. And there's my 10 right there, and that's approximately a negative 45. So my resulting vector is right here. Okay, and mine turns out to be 11. So 1.1 times 10 to the 7th newtons per coulomb at an angle, I'd say that's more than 45, so let's call it 55 degrees. Alright, so that's going to be my estimate. 1.1 times 10 to the 7th. I don't know about this. Let me try this eraser right here. See if we can read it a little bit better. To pen. 1.1 times 10 to the 7th newtons per coulomb at an angle of 55 degrees. Okay, so that's my estimate. I can tell it's a little bit more than 45, but I'm not sure how much. Okay, so that's my graphical estimate. My field then, 1.7 times 10 to the 7th newtons per coulomb at an angle of 90 degrees. This is polar. I'm changing from polar to rectangular. First the x, rectangular x is going to be 0 in the x plus 1.7 times 10 to the 7th in the y. And then my second field, 1.0 times 10 to the 7th newtons per coulomb as an angle of negative 45 degrees. And then that turns out to be 7.1. Now be careful here. This is 7.1 times 10 to the 6th in the x and a negative 7.1 times 10 to the 6th in the y. So when I add those together, remember this was polar changing to rectangular x, polar changing to rectangular y. Now I add my x's and add my y's, and I'll get 7.1 times 10 to the 6th in the x plus 9.9 times 10 to the 6th in the y. If you don't see where that comes from, just put it in your calculators. It's 1.7 times 10 to the 7th minus 0.71 times 10 to the 7th, or turns out to be 9.9 times 10 to the 6th in the y. This is now rectangular. We're going to change the rectangular to polar radius and the rectangular to polar theta, and we end up with 1.2 times 10 to the 7th newtons per coulomb at an angle of 54 degrees. All right, that is your resulting electric field. That is your resulting electrical field. So that's the answer to part A. It's a vector. 1.2 times 10 to the 7th newtons per coulomb. So that answers part A. Now part B, or number 2, what I've got listed on here as number 2, says, let me get this to turn off. Part B wants us to know what force would act on that if I were to place a positive 2.7 millicoulomb charge at A, what force would it experience? Well, we know that the force that a charge experiences is equal to the moving charge, that would be this one, the moving charge times the field. Okay, and the force and the field are going to be in the same direction. Again, this is the field shows the direction a positive charge would move. That's how we decided that this little green one, if I can find it there, that this one was pushing up. Whoops, that's not green. That's how we decided that this one was pushing up and that this one was pulling down. The direction a positive charge would move if it were placed there. This positive would cause a positive charge to move up. This negative would cause a positive charge placed there to be pulled toward it. So the field shows the direction a positive charge would move. All right. From part A, we found that the field, that's not red, come back here. Okay, we found that the field was equal to 1.2 times 10 to the 7th newtons per coulomb at an angle of 54 degrees. Now if I place a positive 2.7 charge there, then the force that experiences is going to be 2.7 times 10 to the negative 3 times 1.2 times 10 to the 7th newtons per coulomb, and it is a positive charge, so the angle it moves will be at 54 degrees. Maybe 54 degrees. All right, so the force it experiences turns out to be 3.2 times 10 to the 4th newtons, because this is newtons per coulomb times coulombs, so coulombs cancels. 3.2 times 10 to the 4th newtons, because it's a positive charge, that's going to be at 54 degrees. All right. Now the third part asks me for the force that would act on a negative charge. Well, we know the field. Again, the field we found to be 1.2 times 10 to the 7th newtons per coulomb at an angle of 54 degrees. But this angle is the direction a positive charge would move. If I put a negative charge there, instead of moving it at 54 degrees, it's going to go the opposite direction. If I place a negative charge there, negative 1.8, it's going to cause it to move in that direction. And that direction is 54 plus 180, or 234 degrees. 234 degrees. So the force then is the moving charge times the field, or 1.8 times 10 to the negative 3 times 1.2 times 10 to the 7th newtons per coulomb times coulombs equals newtons. But this time, because it's a negative moving charge placed there, it's pulled in the opposite direction than your field lines, so the angle is going to be at 234 degrees. And I believe my calculator told me that was 2.2 times 10 to the 4th newtons at an angle of 234 degrees. And yes, you could also call that a negative 126 degrees. Negative 126 degrees, because you could say 54 minus 180, end up with negative 126. What you cannot say, which I get way too many times, is negative 54 degrees. Okay, it's not negative 54 degrees. That's wrong. Negative 54 degrees is not the opposite of 54 degrees. That's the opposite. This one's the opposite. 234 is in the opposite direction of that one. Okay, so hopefully this helps. Have a good spring break, but don't forget we still have a test the week we get back. Thanks.